Alright class, today's video we're going to be looking at scenarios involving projectile motion in which our object has initial velocity that is going to be angled. So because we're dealing with a velocity vector that's angled, we're dealing with a vector where we're going to have both an x velocity and a y velocity at the very beginning. So when we think about vectors, right, we know all vectors have a magnitude and a direction. There's going to be a bunch of them we'll cover throughout the year. Right? This unit is going to focus on displacement vectors, velocity vectors, and acceleration vectors. Again, later on in the year, we'll introduce forces, momentum, torque. Right? These are all things that are going to be vector quantities. Now, one thing is when we are looking at a vector quantity, oftentimes we'll use this little symbol of a half arrow above the variable. Right? This is basically just denoting that the quantity we're dealing with is going to be a vector. Now there's two kind of ways that we can describe objects that are going to be moving along vectors. So let's say we take this example of a car traveling 50 meters at a 120-degree angle. Right, this kind of given to us, we're given both the magnitude and the direction separately. So let's say we had our kind of standard x comma y coordinate. Right, this car is moving 50 meters at 120-degree angles. Right, 120 degrees is going to be roughly over here, right? So we have a displacement vector here of us traveling 50 meters. Now, the second way that we're going to focus on for this one is what we call our unit vector notation. So instead of thinking about like total distance traveled, which is going to be typically a scalar quantity, at a particular angle, we instead want to figure out what are the actual x and y components of this vector. So our job is basically figure out, as you travel those 50 meters, right, how much of us is taking us along the x direction, how much is taking us along our y direction. So this might be useful instead of maybe having, say, a ship that's traveling in the night at a 20-degree heading north of northwest, right? Maybe we can just say we're traveling X amount to the north, Y amounts going west, right? Basically accomplishing the same sort of thing of how we set up our coordinate system. Now, something we do when we are looking at these kind of X and Y components is just to signify which numerical value is dealing with the x direction versus y direction versus z direction. We use this thing we call our IJK notation. So after a measurement, anytime we see that little I hat, again, the hat is just the little arrow kind of pointing up that's above the I, the J, and the K. Basically just signifying, right, what's our x direction, y direction, and z direction. So when we think about kind of these vectors, right, the ones we'll have for this, are going to be our position or also our displacement vector. Right, basically what we are showing in this case is, right, how far, right, we'll have some numerical value for our x direction. Again, we use the I hat vector to signify x direction. But they might have some value for how far we've gone or where we're located in the y direction. Again, that's going to be our j hat. And then lastly, we have, right, wherever our location is in the z axis, that number followed by k hat. So we can do the same thing splitting up our velocity and accelerations. All right, what's the x component of velocity, y component, z component? Same thing repeated for our accelerations. Now, the reason why we use this unit vector notation is that it makes adding and subtracting vectors very, very simple. So maybe we had some motion where it was broken up into two different legs of a journey. We might have our first displacement vector, then we have a second displacement vector, and we want to ultimately know where does our object start and where does it end at the very end, kind of get the overall total displacement. All we have to do is combine our x components separately from our y components, separately from our z components. So let's say we have some vector A that's A in the x direction, A in the y direction, and A in the z direction. Y on to a vector B that includes its x components, y component, z components. All we do is, right, we basically want to add two x components together. We'll add the two y components together. Then we'll add the two z components together. And again, each of them is going to represent how far we travel in the x direction for the I hat, y direction, j hat, and lastly, z direction, k hat. If this was a subtraction sign instead of a plus sign, so instead we had vector A minus vector B, we would just do AX minus BX, I hat, and so on. So one thing we can do with this is if we are trying to describe, say, an object that is traveling in projectile motion, right, we want to figure out what is our acceleration vector in this unit vector notation. What we introduced before is that we know that in the x direction, we always are going to have an acceleration of 0, so 0 I hat. And then in the y direction, right, we'll always have our negative lowercase g, or negative 9.8. So we can say we'll subtract minus g in the j hat direction. And again, this will then be in our units of meters per second squared. So when we're writing out this vector, right, sometimes we'll just simplify it. If we have something that is going to be, in this case, like 0 I hat, we can just get rid of it. We can say our acceleration for an object in projectile motion is just going to be negative g j hat, where again, g is just going to be our value of 9.8. So how this is all going to relate to our projectile motion if something has an angled velocity, typically what they're going to do is give us like the magnitude and the direction of our starting speed. And what we'll have to do is then actually figure out what's the x and the y components to this. So we'll have to use information about our trigonometry. Again, if we have some angle theta here, typically we're giving what we call the angle of inclination. Sometimes it'll just be called like the launch angle of an object, where, again, we'll have our adjacent side, opposite side, and hypotenuse. We'll have to kind of use our sine, cosine, tangents to figure this out. So typically, let's say along our hypotenuse, right, that's going to be what our speed is going to be described as. So let's say we have our velocity or our speed is given to us as maybe it's 30 meters per second, and maybe we're being launched at a 45-degree angle, just as a scenario. So our job is then to figure out the x and the y components of that speed. So for the x direction, again, in this particular case, if we're given that angle shown in the picture, our x direction is going to be along our adjacent side of the angle, and then the y direction, that's going to be along our opposite side of the angle. So if we're trying to figure out what that velocity is in the x direction, because we're dealing with our adjacent side, so we have to use kind of our cosine here. So if we do cosine of that angle theta, we know it's going to be our adjacent side, which is going to be our velocity in the x direction, divided by our hypotenuse, which is our overall speed. So solving this for our velocity in the x direction, again, we'll multiply v to both sides. This is how we get our velocity in the x direction is going to be equal to v, so the speed, multiplied by the cosine of angle theta. Process the same for the y direction. Okay, because we're dealing with our opposite, we'll now have to use sine. So we can say by definition, sine of theta is going to be equal to our opposite side. So that's going to be v in the y direction, divided by our hypotenuse, which is going to be our overall speed. And again, solving for that velocity in the y direction, we're going to get our v sine theta. So this is how we'll break up our initial velocity in these scenarios. So for our example question we're going to look at, This is taken from an old AP FRQ. Again, we'll ignore part C through F just because it's dealing with information we'll cover in later units. But what we have is that we have this small dart of mass 0.02 kilograms, launched at a 30-degree angle. It eventually is going to hit this block that's attached to our pendulum. And eventually, again, later information, we basically have a ballistic pendulum where that mass hits the block, then they both will move up together. But we're going to be focused just for this initial projectile motion part. So one thing that we're told from this is that we're basically looking at this point at which our projectile reaches the highest point along its path and is moving horizontally as then again goes into decline and stick to the wooden block. So if we're trying to figure out the speed of the dart just before it strikes the block, right, basically what that's saying is we want to know what is our velocity at that top point. So what we can do with this is, right, we're basically going to set up again our X and Y projectile motion table. And one thing just to get a little bit extra practice here, we'll also set up what we will refer to as our unit vector notation, just to kind of get in the habit of being a little bit more familiar with how we can look at, I should say, unit vector notation. Again, just to get in the habit of seeing these kind of like I hat, J hat symbols here. So we'll still have our same starting position. We'll have our final position, initial velocity, final velocity, acceleration, and time. And with this, we're basically saying that our final point at which we're looking at this is when the projectile is going to reach its maximum height. So one important thing that we can kind of point out from here is that as it reaches its highest point, we're told it's moving horizontally. At the highest point, what happens is that we end up having a velocity in the y direction that's equal to 0, again, at that maximum height spot. So if we think about our x direction, we're starting off at x coordinate of 0 meters. Ultimately, what we're trying to do and figure out in part B is figure out this horizontal distance d that we travel between our dart launching and where we are when we reach that maximum height. So right now, we really don't know what that variable d is. For our y direction, again, we're starting off from ground level, so we'll have initial height of 0. And at the moment, we don't know what that height is above the ground that we end up reaching. So this will be unknown for us. So if we want to, in unit vector notation for our initial position, we can say this can be 0 I hat plus 0 j hat meters. Again, for our final position vector, really don't have too much information right now, but according to the variables we showed in here, let's just say we'll be traveling some distance. We'll be at location D in that I hat direction for our x coordinate, and then we don't actually know what our y coordinate is either. We can kind of leave that blank for now. Now with our initial velocity here, again, we know we're traveling at this rate of 10 meters per second at our angle of 30 degrees. So that means that our velocity in the x direction, again, that's going to be equal to our overall speed multiplied by the cosine of our launch angle. So we'll have 10 cosine 30 degrees. The velocity in the y direction, that's going to be our speed of 10 multiplied by sine of our angle of 30 degrees. Now from here, again, if you wanted to actually get the numerical value, you could. For now, we'll just kind of leave in terms of 10 cosine 30 and 10 sine 30. So initial velocity in the x direction, we'll have 10 cosine 30 degrees. The y direction will have 10 sine 30 degrees. So unit vector notation, we'll have 10 cosine 30 degrees I hat plus 10 cosine 30 degrees j hat, again with our units of meters per second. For our final velocity, again, we know anytime we're dealing with projectile motion, our acceleration is going to be 0 meters per second squared in the x direction. It's going to be negative 9.8 meters per second squared in the y direction. So basically what this means for us is that our velocity in the x direction is going to be a constant value. So it's going to still be our 10 cosine 30 degrees. And then our y velocity, again, at that maximum height point, key thing is we say our velocity is 0 in the y direction at our maximum height. We are only traveling horizontally at that point. So our final velocity is just going to be 10 cosine 30 degrees I hat plus 0 j hat meters per second. Again, acceleration, what we went over before, we'll have 0 I hat minus 9.8 j hat meters per second squared. And for right now, it is unknown how long it's going to take us to get there. And again, since time is scalar, there's not going to be any sort of vector notation for time. So now that we kind of have our information organized, all right, we're trying to figure out the speed just before we strike the block. So that's going to be our final speed at this point. Again, we know our velocity in the x direction is going to be our 10 cosine 30 we have from our table here. And again, anytime we're taking cosine of an angle, we just want to make sure our calculator is in the proper degree mode. So you might have to switch it off of radian mode. But if we do 10 cosine 30 degrees, that is going to give us 8.66 meters per second. And again, our velocity in the y direction, we know is going to be 0 at the max height. So combining these two to get the overall magnitude, we're just going to have a speed of 8.66 meters per second. If we're then looking at part B, right, trying to figure out the horizontal distance d we travel, one thing that's very commonly occurs in these problems is that in order to first find the distance we travel in the x direction, we need to know how much time, how long we're traveling for. So our first step we want to do is we want to first solve for time. And we can solve for time by looking at our values in the y column. So in the y direction, we don't actually know the final height we reach, so we really can't use anything that includes final position. But we do know our final velocity, our initial velocity, our acceleration. Last thing we need to have information about is going to be time. So we can use our kinematic equation that our final velocity is equal to our initial velocity added to our acceleration multiplied by time. So our final velocity in the y direction we're given is going to be 0. Our initial velocity we had as 10 sine 30 degrees. Then we're adding it to our acceleration is going to be negative 9.8. Multiplying this by t. So simplifying this a little bit, so 10 sine 30 degrees is going to give us 5. If we add over our 9.8t to the left side, we'll have 9.8t is equal to 5. Divide both sides by our 9.8. We're going to get a time of 0.51 seconds. So now that we know we have our time of 0.51 seconds, we can then look at our x direction here. Right, using values where we now know this time is 0.51. And to figure out how far we travel, again, we have time information, we have acceleration information, initial velocity. So from here, we can use our final position equal to initial position plus initial velocity multiplied by time plus 1/2 times our acceleration multiplied by t squared. So final position, that's going to be given as this horizontal distance d. Our initial position was 0. Our initial velocity was our 10 cosine 30 degrees. Now multiplying that by our time of our 0.51 seconds. Just add to our 1/2 times our acceleration is 0, multiplied by our 0.51 seconds squared. Again, that last 1/2 at squared term just cancels out. So when we multiply our 10 cosine 30 degrees by our 0.51, that's going to give us a total distance traveled of 4.42 meters.